Hi, this is an explanation for problem number 68 in chapter 11. This problem reads, driving on asphalt roads entails very little rolling resistance, so most of the energy of the engine goes to overcoming air resistance. But driving slowly in dry sand is another story. If a 1,500 kilogram car is driven in the sand at 5 meters per second, the coefficient of rolling friction is 0.06. In this case, nearly all of the energy that the car uses to move goes to overcoming rolling friction, so you can ignore air drag in this problem. Part A then says, what propulsion force is needed to keep the car moving forward at a constant speed? Now, to find propulsion force, we're going to utilize an equation that is the net forces equal the propulsion force times the F of R. Now, in this case, because the car is moving at a constant velocity, we know that the net force on the car must be 0. So we can go ahead and plug in 0 for F net, and we're going to be left with 0 equals F prop minus F of R. If we subtract F of R, or if we add F of R over to the other side of the equation, we're left with F prop equals F of R. Now F of R is equal to U of R times mass times gravity. So we're given all these in the problem. Gravity, of course, is a constant 9.8. The car weighs 1,500 kilograms, and our value right here is going to be 0.06. If we multiply these three together, we're going to be left with 882 newtons as our F propulsion. So that's part A. Part B then asks, what power is required for propulsion at 5 meters per second? This is a pretty simple calculation. So power is equal to F prop times V. So our velocity is 5 meters per second. We already calculated F prop is 882, so we multiply those two together and we're going to be left with 4,410 watts. Part C then asks, if the car gets 15 miles per gallon when driving on sand, what is the car's efficiency? 1 gallon of gasoline contains 1.4 times 10 to the 8th joules of chemical energy. Okay, so in part C, we're simply going to multiply the 882 newtons by the 15 miles per gallon that we're getting and 1,609 miles per gallon. We're going to multiply these together. We're going to come out to 2.13 times 10 to the 7th joules, which then we're going to divide that number by what problem C told us. A gallon of gasoline contains 1.4 times 10 to the 8th joules of chemical energy. When you divide that and then multiply it by 100, we're left with 15.2% efficiency.